Okay, welcome back. Logistical updates. Quiz 2 is up, like it's online. I pushed off due date till next week, so there's actually time to look at it and not just like scramble through and, I don't know, just gobble or just chat GPT it, like how do I do dynamics? What is it? You don't use it? Yeah. It's not super helpful for a lot. Have you asked it to do a free body diagram for you? No? Oh, it is like just ridiculous in the most obscene way. Like it's like if you asked a graphic designer to just like draw some arrows for me anywhere, just wherever you want, and they're just all over the place. Stuff is going in circles, but it's not torque, it's like forces. There's positions, there's velocities. We'll try it some other time. So quiz 2 and then project 2. Project 2 is the main thing that we have today, like getting that up and running, trying that one out. Sound like a plan? Cool. I know on Wednesday I ran over time. Thanks for staying. We only talked about like one question, so I didn't get to like add the other ones that people were working on. There were some other ideas of like 4-bar linkages and that kind of stuff. 4-bar linkage we're going to deep dive into with this project anyway, so we'll get like some working knowledge there. Because that was kind of the last thing we did in the homework. So I have NanoHub up and running, I'm logged in, and to start I'll just give a tour of kind of like this is the way things run if you do nothing. At least I think. Let me double check that it's all back to normal. 0.95 over 1 degree. Try that. Okay, yeah, so we'll do a tour and kind of main Jupyter mechanics of stuff is like you can run the notebook in any order you want. Like I could go to the bottom and try to run something, but there are variables that haven't been defined yet. So if you try to like make a graph that's there and just update something and not run it, it won't really work. The quick way of just like, hey, run everything for me, like define everything, import all the variables that I want. You can say kernel restart run all, and that'll start at the top, run all the way down to the bottom, and everything gets updated. So that's one way that you can use Jupyter Notebooks. Like if someone sends you one and says, hey, can you look at this analysis for me? That's a good way to start. It's like restart run all. If you get errors, then it's like, all right, something went wrong along the way. Like, it's nothing that I did, it was just because that started. But I'm gonna start from the top, run my way down. No, get rid of that, there we go. So I ran that. The goal here for this 4-bar linkage is that you're going to create your own 4-bar linkage design. It can be anything that you want it to be. Anything. That's like, my kids do that. Rock, paper, scissors, shoot, anything you want to do. And you can like, lava, or bunny, rock. So anything, literally anything. Sky is not the limit, because you could build something for space. The default is just a 25 centimeter crank arm with 1 meter and 1 meter rocker and connector arm. So this would be like a pretty large kind of thing, like something that's sort of oscillating, maybe a pump or something. It doesn't have like a defined like use in this case. It's just a 4-bar linkage to show you that how the analysis works. In here, this code, so the lines above it are kind of like what that design is supposed to be. This is where it's actually defined. So I'm saying 3 links, 1, 2, 3, 25, 1, and 1, and then this A1 doesn't really affect anything, but then DX and DY are telling us how far away is that other fixed point. So we have the origin that's at 0, 0, and then we have some other point that we can put wherever we want. So I put it at 0 and 95 centimeters. Then there's this F bar. Any guesses as to what this thing is? F bar. Like what is that? Do you know, have you seen lambda before in Python? What does lambda do? Just as a, like the actual like function lambda. Someone throws it in their code, what did it do? That was a CSE 1010 that was relegated to recycled in. So lambdas create functions, and that's all they, and it's, you can use that DEF to say like define a function. Lambdas are a quick way to, like, in one line, I have a whole function defined. I don't need to define like return statements or anything like that. So it's a function, it's returning 2 values. And those 2 values are my position constraints. Do I have it written out here? No, I don't have it here. So it's the constraints that, coming back up, L1 sine plus L2 sine theta 2 minus L3 sine theta 3 minus dy. So all the steps that I took up have to equal all the steps that I took down. And then same thing with the cosine steps. All the steps that I take left and right have to add up to steps that I took left or right. So it's just it's giving Python like, hey, this function always needs to be true. And if it's not true, then I don't have a 4-bar linkage. I just have like random numbers thrown in there. So I'll define motion of the crank. I'll just go from 0 to 360. I did change, I forget what the number is here. If you say 0 to 360 and 361 points, then every index is 1 degree. So the crank will move from zero, go all the way 1, 2, 3, 4 until it gets to 360. And then in this loop, and again, we're not really like coding Python here. Like, this tour is just meant to show you like what's happening as you run this code. It's not so that you can like, all right, now go, start from blank slate and start typing away and build your own code. just enough that you know where to look when you want to change things. That's our goal for today, and I mean this class. So we loop through every degree of link 1. So link 1's going to move around in a circle, and we need to figure out what are the angles of links 2 and 3 for every theta. And that's what we did in the homework. It's just we did it for one fixed position. It's like, okay, if this is where my hinges are, what are those other angles, and what are the sines and cosines? Nice part is like when you put it in a for loop like that, you get everything. Like here's theta 1 going from 0 to 2 pi, or 0 to 360, and then theta 2 does a nice, like, not quite a sine wave, but something oscillating, and then theta 3 does the same thing. So the angles are changing. So that's our first one. This one. So here, I copied this one down again. If you want to look at it in degrees instead of radians, it's very hard for me to remember that like 3.14 radians is 180 degrees. I don't think that way. So degrees, most humans prefer to see like how many degrees is the angle. It's usually a little more intuitive. Not quite intuitive. It's still like a weird engineering term. Like, what is that? What's the orientation of this rigid bar? But anyway, so we can change the units. So we have a rad 2 deg, radian 2 degree function. And if I know how long the links are and I know how they're all connected, I can define like where all the hinges are and actually draw like what does this thing look like and where is it moving to. So that's the next part here. So where is hinge A, where is B, where's C, and then P is a midpoint between the crank and the rocker. So right in the middle of link 2. And then it'll catch up in a second. What is this showing? Like there's a blue circle, there's a green.
Yeah, the blue circle is that first point. That line rotates in a circle.
Okay, yep. The path of each of the hinges, yeah.
No, in the green line, the center part of that middle line.
Yeah, and the green, so we have,
And the red part is,
yeah, so hinge A, that's our crank, it just moves around in a circle. And the longer we keep that running, the more it's going to keep going. Hinge B is rocking back and forth. So it never completes like a whole circle, it's always just tracing a small piece. And then meanwhile, this midpoint, that's where you can do, so with that midpoint, you can get some really interesting like engineering design things done. So knee replacements, they look at where that green point is moving and try to match like what is the meniscus? No, meniscus is patella, right? I always forget my anatomy. But there's ACL and PCL kind of connecting. They create a 4-bar linkage where your femur is one of the links and the top of your shin is the other link. And then the ACL, PCL, ideally they don't stretch. They can stretch like they are ligaments, but they're not supposed to. If you stretch them every day, that's how you tear them. So the motion of those 4 bars kind of connected to each other trace out like a green path like that. It's not a circle. So the shape of your knee is kind of this like cool thing governed by a 4-bar linkage design. But anyway, so that's why a green path is on there, because you can do lots of cool stuff there. Sorry? Sorry, what?
C is stuck in place.
And then C doesn't move. So there's a yellow line to tell you like where C went. There shouldn't be a yellow line because that means that something was broken. It's supposed to be just nothing there. It always moves a little bit, like 10 to the negative 16, but that's okay. That's close enough to 0. And then same thing as we did in the homework. If we know what constraints on position are, we can define constraints on velocity. And now we know everything, like from start to finish, an entire cycle, where this thing is and where all the links are. We can also figure out how fast everything's moving. So now, instead of just solving like a single point in time, I can look at, if I'm driving at 1 radian per second, how fast are the other two? How fast is my rocker moving? How fast is my connector arm moving? Or at least like how fast they're rotating. So let's look at like so theta 3, this yellow line, is our rate of rotation for that rocker. Based on this graph, what is the max speed that hinge C is doing? That actual hinge, so the hinge C is rocking back and forth. What's its maximum speed based on this graph? You can round, like you don't need, like it's a graph, like you can only get so accurate. Yeah. Radians per second, yeah. 0.2, so how fast is that? Because it's a point in space, how fast is it moving along that curve? Because that's telling you how fast it's rotating, right? So how fast is it moving? It's a trick question. It is it's still 0.2. Well, I mean here, really I would say like 0.4, because that's like negative point, whether it's negative or positive, it's still moving, right? Like if you're moving backwards versus forward, but you move backwards 20 miles an hour, forward 10, your max speed was 20. So here I would say like 0.4, but it's a 1 meter long thing. So 1 meter times 0.4 radians per second is 0.4 meters per second. It's rotation rate times distance gives you speed, how fast you're going. So that's kind of, and again, this was a very quick tour of what's happening. And for the most part, what we're doing is changing these design parameters of like, what does our 4-bar linkage look like? And then going through the same analysis to figure out, is it what we want? Is it doing what we thought it should do? So we have some tools, we can solve for stuff, so we can play around with these things and yeah, get it to do something. So if you're trying to like drill for oil, like an oil pump, these numbers are probably like 5 to 10 times too small, right? Oil pumps are going to be tens of meters tall. Maybe your crank arm is like a 1 meter crank arm, and then everything else is like bigger. If you're trying to do a knee replacement, all these values are probably like 100 times too big. I don't know. They're usually centimeter size, like ACL, PCL. Young's modulus. I don't know if I do have Young's modulus notebooks right now. All right, what do you want to change first? Let's try one change and see what happens. We'll make a hypothesis. Like if I change this, it will lead to something. If we make link 1 bigger, what's going to happen to bigger or smaller? I don't, in either way, but what's going to happen to like the speed of our rocker? Longer is faster? What do we think? Yeah? So it'll move, so before we said like max speed was like 0.4 meters per second for hinge C. So so if we make this one bigger, it should move faster. Makes sense? Makes sense to me. You have a bigger circle, you're moving around same rotation rate, everything should move a little faster. How big do you want to make it? How big? Double it? Playing it safe. Bigger is better, right? What do you think? Make it 1? How does 1 sound? Is that one good? 1? 4 times. So we'll make it 1. Everything's 1. Already we see something pretty different. We didn't get any I did kind of expect a warning, but we didn't get any warnings. So it does seem like we can solve it. But the angles are different. Something's happening. So we'll keep running. Just calculate where everything is. How does this look? Almost like a Venn diagram, yeah. Why does it look like a Venn diagram? We didn't have that before.
Well, I guess that was made the same way, so now it's over it.
Now it's kind of, yeah. Yeah, so really, before, like, we had this blue circle, and then this was only like an arc. You could only get part of it, but now we're almost doing the whole thing, like almost doing that whole circle with it. Yeah, and we left everything else the same. We do have this cool like heart shape in the middle, so that one's fun. Great for Valentine's Day, so hang on to this one for the next few months until you're ready. You can build it out of Legos. And let's show like, what does it look like at 90 degrees? Kind of flips over like that. Or if we look at maybe 45 degrees. So we have this weird kind of like flip-flapping like thing that as it comes around, like it creates an X when it's up top and then flips around quickly to go around that way. So let's find the speeds. Sure enough, we do have things moving a lot faster. So a 1 meter hinge C moving at 20 radians per second, 1 meter away, talking 20 meters per second, which is 40-ish miles an hour, right? It's pretty fast. It's like swinging an axe. Maybe that's what you want. Maybe this is like a hatchet thrower. I don't know. All right, let's break it. let's make this one like 1.1, just a little bit longer, because bigger's better. This is where, so at some point you're going to violate, at least if you're just kind of throwing random numbers in there, that there might be points where you break the constraints and it'll give you this big pink warning box of like, hey, things aren't looking good, like the Jacobian evaluations. It's all warnings. Like, it still gave you an answer, so you can just ignore it and be like, da-da-da. You can keep going. It's just it's telling you that things didn't work out, but it's like, I don't care. You'll see things like this where the curves are no longer smooth, so something's weird there. Like, I don't think that's a normal thing to happen. Then as we look at like link locations, now we start seeing some other weird things. Like here it's kind of small. I should have made it bigger. But this yellow hinge is moving. And if that's moving, it's not moving to like we don't have a constraint that says like hinge C can move in this direction. So it's just randomly finding what is the best place to put hinge C. So it's moving it around. And then we really get some noise in the speeds where everything is just, there's probably not an application that you can actually build something moving 30,000 meters per second because you like hooked up your 4-bar linkage wrong. Something's wrong. You did something weird. Okay, so now it's your turn. Choose a geometry. You have like laid out things that will plot the motion. You can plot the speeds, and then you're trying to wrap up. It might take a few iterations to get like something that you want to do, something that you wanted to do, but your goal is like using the information that you can see. And if you're trying to get more information out of it, you can ask me. Like if you want different results, we can always find something. But then wrap up, like why do these graphs say that you chose the right geometry or the right mounting points, those kind of things. So a little bit of engineering analysis. And then learning along the way. That could be things like link 1 can't be longer than, or link 1, 2, 3 can only be a certain amount of length. Like you can't, if you want a crank arm, you can't have everything add up to bigger than the connecting locations or smaller, right? Like you can't have mounting points 10 meters away but only 3 meters worth of connectors. And yeah, or things like we just noticed. The bigger link 1 is, the faster everything moves. Cool. Questions so far? It's a whirlwind tour. Go back up to the top. And there's a few examples here, like windshield wipers or watt linkage, all sorts of, there's a ton of other examples where you could use this. Cool. I'm going to check in, see what's going on. Any ideas for like applications that you want to see? Yeah. Yeah, those are little, so I think those are just kind of like gear down. Like one, I think it's all one shaft. But like using a crane, like a design of like how big the crane can be, and then how fast you're gonna spin it. It's a not what it is. It's the study of like using things that humans can use. No, like does it feel right when you use it? Anyway, ergonomic. Thank you. Yeah, so it's an ergonomic 4-bar linkage problem because you have a crank that a human is spinning, and then so the crank arm is the design, and then the connector arm is your forearm, and the rocker arm is your bicep. So your bicep is providing all the power to crank. Yeah, because like you could design, ideally you would have like bigger crank arms because you get more torque with the same amount of force personally. But if your crank arm is doing this, it's like it becomes like almost untenable to actually run that machine. So that's why most crank arms are all handheld sort of things. They always less than your forearm length, so you can actually use it. Yeah. Yeah, yeah.
I mean, it's just like, I didn't imagine it having that same type of motion because this seems like so like base like that. And the other part of it just like one blows. Yeah, so it's
Yeah. Like the cool part for like a device like that is like to get the same amount of mechanical advantage from that like if you took that 4-bar and just turned it into like a lever, you have like a wrench like this. Yeah, because there's so much mechanical advantage in just those little like link things. Yeah. No, you can change them to anything. Even the units, like you can say, I want the same thing, but all these units are geared to this or something. What were you kind of looking at?
I was just like, what if I made like units?
Oh, okay. Yeah. Yeah, what would that do?
Probably be like, oh, like you know how
Yeah.
so
Okay.
I can attach these guys so that when you walk over it triggers.
Okay. Using 4-bar for the triggering. Yeah. Yeah. One nice thing about like why you want a 4-bar trigger versus just like a lot of triggers are just but if you have a 4-bar, you can still have the same torquing spring, but now as you push it, it's always parallel. Yeah.
So it's not
Yeah, like it wouldn't feel like a diving board as you went across it. It's like press, stay down, and pop back up. Yeah.
There's not point in making this.
Oh yeah, nice. That one's cool. It is 4-bar.
So it's like used to use it.
Sorry.
Used to use it.
It also seen side like rather than
That was not sorry at all. It's more color.
oh does it?
This one's
That was pretty cool.
and they're recommended.
Oh yeah, and even those like
Like, I don't know what this is, but it's what this is.
1 degree is just not enough. I need more. Then kind of started. What are the two inputs? Control everything. It would just be, it would be cool. It's just, it's a different analysis.
Okay.
Yeah. Yeah. Like here, the way that I was kind of looking at it, this is this.
Oh, I see. Yeah. So also be
Now this is more like that looks like suspension. Yes.
yeah.
Alright. Breaking stuff. Breaking stuff.
I've just been kind of like, I looked at like typical dimensions of modifications and switching those numbers in and out. That's a pretty interesting stuff.
I mean, they can be anywhere from millimeters to tens of millimeters.
Yeah. And I've kind of noticed like as you like vary these, it's like weird.
Yeah.
So like, no.
Yep. Yeah, and see how like these things are so long when this gets to yanking it that way. So one way to fix it is just change that dx, make it closer together.
Yeah, it should be like 20.
At least if you don't want to. Now it kind of looks like what we started with, just everything's small. Yeah, the change it. Yeah, so there's something like you're kind of stumbling into something that people call fractional fractional condition. If you have these three links and you mount them here, they have to. There's only certain conditions that you can have out of a certain language. If it's too far apart, you can't connect them.
Sorry. That's okay. Is this what I want to look like? Is it? Because I'm like trying to apply these formulas that I have to really fully understand. The givens. Like, that's what I'm getting when I want to like pictures this circle here.
I have a circle. Because that one's showing easy that moves around.
Yeah.
Almost all the time, your brain is a circle.
Okay.
Sometimes like some other people talk about positioning things. Very often
Yeah, yeah.
or like
It's also upside down.
yeah, yeah, this one's kind of like upside down.
Yeah.
So the brain
Yeah, of course. What?
Okay, so I'm just pasting things on the wall so that it's easy for them to figure out their seats.
Okay.
I mean, so I love
Can you paste it on this side? This is row.
Of every row?
Yeah, you probably can't go
Do you
tell.
want me to take all of them or just?
Yeah, I'll just write the numbers.
Okay.
And then I'll give it to you.
So usually what like swings white shots have to do is you're limited in how many teeth, because the number of teeth on each one, you only have so many teeth per circumference. So like 15 to 25 is the two. 19. Number two would be like 1 point something, like 9 something like that, right? Okay. So you can, one way you could do it is figure out, all right, what can I have? How many teeth can I have? And you kind of limit it to like the back, go 11 to 15. Yeah. Well, you can do 9. Yeah. But 9 to 15. Yeah. And then up front you can have like 34, 42, like up to about base yeah. So that's one thing. It's like you can get weird, irrational numbers with gear ratio. Not irrational, but like repeating. Yeah. But you are limited to the chains. I mean, if you want to change it, you can resubmit as many times. So if you made a mistake, then you can resubmit. Yeah, that's fine. Alright, thanks. Sorry, I didn't get it. Yeah, yeah. Yeah. Those, a lot of those are, yeah, so those are kind of like, almost like pulley systems. So they're definitely like a lot of kinematics involved because you kind of like change, yeah, like gear ratio, like you have one big, okay, here's my RPM of my engine, and then alternator, I want it to be a little slower, so a smaller one, bigger fan, but so that one definitely kinematics, but a little different, like not the same here. But in terms of like automotive, it's like the king of everything. There's so many languages. Suspension, every piece of suspension is all for running. There's a few spots where like you can just have a hinge thing moving. Most of the time, some form bar. So that like one of the big things would be cars bouncing up and down. If you like one thing you could do is just have the axle, springs attached to the axle and let it end. But now every time you can bump it fewer pieces. Okay, well now I'm wearing out the inside of the wheel, right? So put a 4-bar linkage there, so we can either let it cancel